Imagine you must build a binary array using exactly 0 zeros and 1 ones. But there's a catch. You're not allowed to place more than limit identical numbers consecutively. Sounds simple, until you realize the number of possible arrays grows exponentially. Brute force? Impossible. But with one clever dynamic programming trick, we can solve it in O of n squared time. Let's break it down. The problem is called find all possible stable binary arrays 1. We are given 3 numbers. 0, the number of zeros, 1, the number of ones, and limit, the maximum number of consecutive identical numbers allowed. A binary array is considered stable if no more than limit zeros appear consecutively, and no more than limit ones appear consecutively. Our task is simple. Count all possible valid arrays. Let's look at an example. 0 equals 2, 1 equals 1, limit equals 1. Possible arrays include 0, 1, 0, 1, 0, 1, but arrays like 0, 0, 1, 1, 1, 0 are invalid because they contain 2 consecutive identical numbers. So the final answer is 2. Now here's the key observation. When constructing the array, only 3 things matter. How many zeros have been used? And what was the last number placed? So we define a dynamic programming state. XML ID equals dpb1x2. Now we define our dynamic programming states. First, dp state ij0. This represents the number of arrays using i0s and j1s, ending with 0. Similarly, we define dp state ij1. This represents arrays that end with 1. These 2 states allow us to track all valid constructions. Now let's look at the transition logic. Suppose we want to place a 0. We append it to arrays that previously used i-1 zeros and j1s. So the transition becomes dp of ij0 equals dp of i-1j0 plus dp of i-1j1. But wait, this might create more than limit consecutive zeros. So we remove the invalid sequences. If we already had limit zeros, adding another 0 creates limit plus 1. Those cases must be subtracted. Over 0 equals dp of I minus limit minus 1 comma j ending with 1. We apply the same idea for ones. Over 1 equals dp of I comma j minus limit minus 1 ending with 0. This clever subtraction trick keeps the dynamic programming efficient and memory-friendly. XML ID equals codex1. Now let's look at the implementation. We define a class called solution. Inside it, we implement the function number of stable arrays. The function receives 3 parameters: 0, 1, and limit. First, we define a constant called mod. This is 10 to the power 9 plus 7. We use it to prevent integer overflow. Next, we initialize a 3-dimensional dynamic programming array. dp indexed by zeros used, ones used, and the last number placed. Now we handle the base cases. If we only place zeros, we can fill up to the minimum of 0 and limit. Each of those states ends with 0. Similarly, if we only place ones, we fill up to the minimum of 1 and limit. Each of those states ends with 1. Next comes the main dynamic programming loops. We iterate over all possible counts of zeros and ones. For every state, we compute 2 values: the number of arrays ending with 0, and the number of arrays ending with 1. But before updating the state, we calculate invalid sequences. If adding another 0 exceeds the limit, we subtract those cases. This value is stored in over 0. Likewise, if adding another 1 exceeds the limit, we subtract those cases. This value is stored in over 1. Then we apply the dynamic programming transitions. Arrays ending with 0 come from previous states with 1 fewer 0. Arrays ending with 1 come from previous states with 1 fewer 1. Finally, we return the result: the sum of arrays ending with 0 and arrays ending with 1. All taken modulo 10 to the power 9 plus 7. Now let's analyze the complexity. The time complexity is O of 0 multiplied by 1. Because we iterate through every possible combination of zeros and ones. The space complexity is also O of 0 multiplied by 1. Since we store results for each dynamic programming state. This is optimal for the given constraints. This problem teaches a powerful dynamic programming technique. First, add all possible constructions. Then subtract the invalid cases. This trick appears in many problems involving constrained sequences, consecutive limits, and combinatorial counting. Once you master this idea, many medium and hard dynamic programming problems become much easier. If this explanation helped you understand the pattern behind this problem, subscribe for more clear LeetCode breakdowns that make hard problems simple.